Okay, so welcome. This is actually our first webinar of the spring semester. We are a little behind the times. But I did want to just before we jump straight into the presentation for today, I did want to mention that there are several pickup things going on. You can find out more details on the pickup webpage, but the biggest one to be aware of is there's a series of regional pickup workshops that will be coming to somewhere fairly near you. The first one is scheduled for the LA area in May. So again, you can find more details on the pickup webpage, but I know that will make some of the pickup organizers happy to know that I mentioned that. Okay, so today we get to hear from Paul Tjossem and Charlotte Christensen from Grinnell College, who are going to tell us about their class slash textbook that integrates computational physics with the mechanics course there at Grinnell. So Charlotte and Paul, take it away.
All right, thanks, Nick, for inviting us. Uh, we've entitled this Tech Meets Mech, bringing mechanics students up to code. And it's not really, I'm not here to hawk a textbook or anything, but I'd like to tell you a little bit about our project, how it got started, and what we're doing with it. You? Ah. So the motivation for incorporating Python into physics comes from a survey we did a dozen years ago, and we asked alums, what can we do for you? How could we improve our department? And one of the strong uh, comments was about needing more programming in physics. So we'd already had a computational physics course that had been running for about 30 years, but that didn't cover everybody. So they really wanted more structured programming for upper level courses and labs, and so that they could make a better transition to graduate school or industry. At Grinnell, physics has no required computer science. We require 4 math courses through differential equations, and we have a great CS department, an award-winning CS curriculum. But it's a long road to get to where you could actually analyze data and model mechanical systems or E&M. And it would take our students at least 2 courses, and they still wouldn't be able to do any of those things directly. Finally, why mechanics? Uh, we thought, well, this is where the majors are born or created or declare. And so this is a pivotal moment for them. And the mechanics course has always been rather pencil and paper, analytical. And we thought, well, if we could add a lab to this, unbeknownst to the professor at the time, not really, but what we would do is be able to bring visualization and modeling to topics in classical mechanics, many body orbits, non-inertial reference frames, chaos in nonlinear driven systems. So there's lots to play with.
So I'll talk a little bit about the challenges to overcome. So we had this plan of setting up a lab associated with the sophomore level mechanics course that would be taught in Python that would help give students some background in programming. And some of the initial challenges was really the students have a wide range of backgrounds. So some of our physics majors are dual CS and physics majors. Some of them have been engaged in programming at a high level since they were in high school students and earlier. But then some other of our students have intentionally avoided programming and have little to no background at all. So somehow we wanted to serve this entire range of students. We were also concerned about how do you scale this class to work with a number of students. At Grinnell, we're fortunate to have reasonably small class sizes. The sophomore level mechanics course gets into the low 30s though. And we wanted to be able to get something that was sustainable as opposed to adding a separate course with more teaching requirements but still something that would allow us to give enough individualized instruction to students. So we set it on the lab as a way to serve a decent number of students at a relatively small teaching cost. So this works out to about 16 students per lab. The other side of this enrollment management is the staffing. This is taught by professors. Some of us in the physics department are very enthusiastic about programming, but we also wanted a course that would be accessible to physics professors who do not do much programming as part of their research and maybe have not taught programming before. And because of that, we've included a lot of instructor guidance. And then the final thing we were up against was insecurities around computing. So this comes from the students, especially those who I mentioned earlier, who didn't have a lot of programming background. And these insecurities come out when they are next to other students who are very confident in their programming. So we needed a course that would allow students who are entering a lot of programming fear to still be able to learn the material and grow from it. Not on this slide, but also something we thought about was how do we coordinate with the computer science department? And basically the way we've done this is we've left them their territory, and we sell this course not as a computer science course. It is definitely not a computer science course. It doesn't do much in regards to algorithms, but rather a course that gives them a jump start into programming. There are basically two different learning objectives for this lab. There are programming learning objectives, which I've listed on the left, and then there's physics content learning objectives. Our hope is that this lab supports the physics that the students are learning in their mechanics course. So we wanted to incorporate those throughout the semester. In regards to the primary programming learning objectives, we group these by color. So there's some information on data types, variables, NumPy arrays. There's also some content on controlling programming flow, functions, loops, and logic. A lot of work is done in visualization. This includes plotting and animations. And then there's work on data analysis and simulating. So fitting data, input and output, zero finding numerical integration being the big ones. And then finally, since we chose to teach this in Python, it would have been a shame to end the class without having anything about classes or modules. So we do include some information about that as well. In regards to the physics content, the content of the course uses John Taylor's classical mechanics, and we follow that structure pretty closely. This curricula doesn't need to fit with that textbook, but it works really well. And some of the physics situations we investigate are air resistance, rockets, energy, oscillators of many different types, the brachistochrome problem, gravitational orbits, non-inertial reference frames, rigid body rotation, and we end with chaos.
How appropriate.
So this is a flowchart, which you probably can't see wonderfully on your screen, but I just wanted to show this and actually the next slide about how we organize these units. So each of these rectangles is one unit and would typically be done in one lecture period for us. And they relate to each other. There is kind of a preferred direction of motion through it, and the arrows demonstrate that. Right here, you can see that we've outlined several different entry points. So this first entry point would be for new programmers, and new programmers would start right away with an introduction to Python, followed by a unit on Taylor series and including information on loops and functions. So this is where we start our Grinnell students. We don't assume any sort of programming background. However, for situations in which students do enter with programming backgrounds, they can probably skip right away to entry point A, which is about numerical integration, or entry point B for experienced programmers if they aren't interested in the algorithm for numerical integration, but just want to use the code that Python provides. You'll also notice on each of these, I have some blue text and some green text. So the green text, that's the physics that's covered, and the blue text are the programming skills. So this takes students through the first few units, and then we get all of this, which is a pretty confusing chart. This is meant to be divided across 2 pages. You read top to bottom on the left and then top to bottom on the right. And one thing I want to point out is that there's no way a class would cover all of this material, at least not how we teach it at Grinnell. We select about 12 of the units overall, and that allows us time to also give the students a final project at the end. Because we don't anticipate that most places would want to do all of this work, we show the different dependencies. So I'm going to highlight one section down here. This is the very end when the students are learning about chaos. You see they start with this unit in the middle. It's the damp-driven pendulum. So that's the system. And the first thing they need to do is actually model the system. There's some analysis of it, including peak finding and arrays of data and polynomial fits. From that point, they could end the unit. That would be sufficient. Or they could move to the left and bottom to creating a bifurcation diagram. Or they could move to the state space orbits and Poincare sections listed on the right. So those dark gray arrows show a necessary dependency where you need to have modeled the damp-driven pendulum before you plot the Poincare section. And the light blue and green arrows show a trend of information, but not a necessary connection. So it's possible to complete the Poincare unit without having generated a bifurcation diagram. And actually, that's pretty common within our curriculum.
Oh, and please, because the chat is open, feel free to interrupt us at any time as we go forward. At Grinnell, I want to talk a little bit about the implementation. So just Charlotte has touched on the mention that it's in a standalone lab. It's all done in Ipython notebooks, Jupyter notebooks, with a standard Anaconda distribution, and we don't need to add anything to that. We do it as a weekly lab, so we might get about 10 of them done in a semester. And then we hold it to 16 students per section. We have enough computers that we could squeeze a little bit more out of it. We give them 2 monitors because, well, then they can, it worked during social distancing for COVID, but also they can look at a screen a little up close and personal. We always do it as paired programming, and because that's a really good paradigm. And sharing the mouse and the keyboard and looking for, so there isn't primarily a typist in this. We also try to rotate the groups so that students aren't stuck with their roles. And I think having potential physics majors learning how to work with everybody else is a very valuable thing. We rely heavily on our student assistants. And so the early years were a little iffy. But then we've started this in 2015. So we've had some experience. And so we have students who've been through the class and are typically juniors or seniors. And they are very helpful to us because they know where they tripped up way back in the day. And occasionally we get a CS major who's interested in Python because we don't teach Python here. In fact, we don't teach any computer language per se. It's not part of our stable. So they learn it on the playground and they bring it to us, and they learn a little physics along the way. It's great. The final projects are pretty freeform. You'll see, I'm going to show you a notebook, just a sample notebook. That looks highly structured and has got little pieces and little cells that they run and things that we've blanked out and they have to fill in. When it gets to the final project, we just say, hey, take an interesting problem and tell me something about it and display it, whether it's a animation or graphs or results, do the physics. And students have done things from multi-stage rockets, orbital transfer mechanics, Hohmann transfers, double pendulum is pretty popular. Animating that's kind of fun. Parametric oscillator and coupled oscillators, etc. Ooh, so here's my first simple example. So this is maybe in week 3. So they've had a little bit of, we did the Taylor series, so that connects with the book, and we've also done things on. Oh, we're slightly ahead, but it doesn't matter. We're looking at the simple pendulum, but large release. So remember that these are this is the first time they've ever approached a pendulum that is not small angle approximation. Okay, once in an intro lab, they'll say, yep, it's different, but they can't actually quantify it. and it's not very satisfying, and we don't have a good model. So here's a typical unit, and we put the objectives there, and I think they follow Charlotte's color scheme indeed. Green is physics, and blue is programming. And you'll see that what we're doing here is simply calculating, simulating large angle release. And we start out with let's see if I can actually scroll this thing worth a darn. And the answer is no, yes. Oh, good. We load in the libraries at the beginning. We always stop and say, okay, give us an analytical solution. Get a piece of paper out and tell us what you know about the simple pendulum. And so they have a little exercise. And you'll note in this exercise, and I'm just trying to highlight, we put some little tags on here. And that exercise, those tags are for a post processor we use to take a working notebook and pith it. And the idea is that students will have to fill in those exercises and show us their work. And so we include that. So everywhere there's a pound slash, hash slash, we remove that in our post processor for the student version. And then if you, so we have them then go on and look at the equation of motion, but with sine theta, we want to make sure that they are getting the appropriate torque and moment of inertia here. And that's why we actually do this with, it looks funny. We have we have a fixed length here, and we're looking for a period of oscillation. That fixed length is not just arbitrary. We actually did an experiment to measure the same, and so they can compare with an experiment in a later unit. So here's the equation of motion. We found that actually if we made the length equal to 1, they had terrible times with the units and dimensionality. So it's very, very handy to put a weird number in there and have them go with it. So let's see if I can run this. Okay, so they define the variables, and so they set that up, and they have to define a derivative function. Students have already done a simple Euler and a leapfrog method, so they know roughly how a numerical integrator works. And so then we get them to define the derivatives. And let's see where we go here. And then we use the CAN solver in SciPy, solve initial value problem. And that works pretty well. If you give it a pretty small tolerance, the solutions are quite nice. So then they integrate it, they plot the trajectory, and here's small angle, and there's not a huge surprise, and you probably can't see it, but here are 2 lines. One of them is a small angle, just a cosine theta, and the other is the numerical simulation. And that's very gratifying that they look the same for angular velocity, and then a state space plot is a nice ellipse. No surprises. They know a little bit about energy, so we might as well have them plot energy as a function of time and make sure that indeed the kinetic energy in red, the potential energy in blue, and the total energy all add up, appropriately, and that's shown on this plot. And they get to learn some nice things about legends and the like on matplotlib. But they've never really changed the angle of a pendulum to see that there's a difference in period. So now they get to calculate at 2 different angles. One of them is 5 degrees. One of them happens to be at 60 degrees. And they get to compare the results. And it's a somewhat subtle, but you'll of course see that the blue one is a little bit faster than the green because the restoring torque isn't quite adequate at 60 degrees. And if they really want to get good at this, we say, well, you could plot a Lissajous pattern. And so these are nice the beauty of a notebook is that you can just stop and say, give me an extra section. And then the rest of this is about trying to get that plot that you saw at the beginning, which is they learn things about events in SciPy's solve IVP, which is we want to know when there are 0 crossings in the angle. So they define an event, they feed that into the integrator, they note that that the zero crossings on these trajectories at low angle, it gives us the 1.8 seconds that they expected. And then what do we have here? Ooh, real time. We're now calculating out, it's a 100-second simulation. They are changing the angle. They obviously have to have learned how to make a loop in Python. And then we get to the end of this, and I think we've hit 89 degrees. And bingo, we get the angle, the period as a function of release angle, and then normalize that. And of course, that's good because later on we will want to know about how do you actually numerically integrate an elliptic integral of the first kind. And you need to know how to normalize to that. Finally, we ask, physicists always bandy around the small angle approximation. And to my theorist colleague, small angle is anything up to 30 degrees. And I wanted to know, well, when is it really important? And so we use a where method, and they figure out how to find where the angle exceeds, where the period exceeds 10%. So I sort of lost that here, but they look in their array and find that it's about 70 degrees. So we all feel comforted if we're happy with 10%. We have some other things that are useful to physicists, like writing data to a file, because we want to compare with an experiment. We want to read that in. So we give them we don't do real data science here. We're not doing pandas. We take the simplest thing, which is save text and load text with a column stack. And so they can get X, Y arrays out. Colab, so let's skip that. Yeah, and I think that we're pretty much here. At the end of each unit, there will be a sort of a, what did you learn out of this? Because we have to get our assessment. And then we include a challenge problem. And in this case, we're simply including damping. And so I just running this quickly, a small amount of damping. We watch the energy fall off, the amplitude fall off, the velocity fall off. We get a state space spiral. And finally, we ask them a question about, well, where did that energy go? And if you look very carefully, you'll see that, of course, it's correlated with where the kinetic energy is maximum. And so they get to look at that. And I'm done. And any questions?
I've actually got a question. So you mentioned Colab. Are you having students use Colab, or are they running these things on their own machines?
That's for Charlotte to answer.
All right, that sounds like my call to take over. Okay, so in this lab setting, we have Python already installed. The students just sit down at a computer. We show them how to open Anaconda Python and how to start a notebook and download the materials. However, students when students do work outside of class, and in later courses, they oftentimes choose to use Google Colab or CoCalc. And so in all of these notebooks, I've included some information on how you get those to work. And it tends to be pretty straightforward, except when it comes to either data storage, because the data that gets written to the cloud. And you have to have some instructions on how to access that data, or movies, because the visualization is happening through a web browser. But we have the notebook set up so they can be run in Colab or CoCalc. Students are also actually pretty good at installing their own version of Anaconda. So it's not unusual for a student to come up to me with a laptop and ask me to look at their code on just in a regular Jupyter notebook installed there. Okay, I'm going to go ahead and move on, but feel free to interrupt with questions. So you saw one notebook, and Paul pointed out a few features of it. Just going to summarize some of the philosophy we have in writing these units. We like to start each notebook with some analytical work, and there's analytical work oftentimes throughout the notebook as well. And this is important for two reasons. One is, again, this is a physics course, and we want the grounding to be in physics. And we want the work that they're doing here to support their support their learning in the mechanics course. And the other reason is that it tends to normalize the class different distribution, because students who are strong on the programming might not necessarily be as strong on the analytic, and vice versa. It gives more opportunities for individual students to contribute to the work. Similarly, we ask for conceptual pencil or paper questions throughout the notebook. You saw there was a checkout at the end of the notebook. Oftentimes there are checkpoints throughout as well, where students are asked to analyze their plots. It's important to us that students don't just look at a plot and say, oh, pretty. We actually want them to think about it. Like you saw the small angle and the large angle release pendula getting out of phase with each other. How long did that take? Does that make sense? And something else you noticed is that there was a challenge problem at the end. Again, recognizing that different students will complete these units at different speeds, we've tried to make them as flexible as possible. So there are challenge problems for the students who speed through the units. There are also exercises within the units that are designated as non-essential. They're shown in gray. And this allows instructors to easily trim out portions from the notebook. This also means that these units are pretty flexible if they were to be assigned in a shorter length class period or as homework. It's kind of clear what are the essential portions. And then finally, the instructor gets the fully worked Jupyter notebook, and the student version has the parts selectively removed using the script. And if you are interested in that, you can reach out to Paul or me. We can provide you with that script to remove anything within #/. All right, I want to show one other example, and this one is on orbits. So let me bring up this notebook. So the one on pendula, that is, as Paul said, probably around week 3, maybe week 4. And now I'm showing you something that students would complete about midway through the course. So these are for orbits, in particular 2 bodies undergoing a gravitational interaction. But there's a little bit at the end where we alter the force between the 2 of them to make it from a 1/r² law to a 1/r⁵ law. And I'll illustrate with 5/2. Yes. And I'll illustrate what happens there. So this is a student version to give you a sense of the types of materials that students are provided with midway through the course. So they start again with an analytic calculation. In this case, it's a calculation to figure out the initial conditions that will result in a circular orbit. We give them the variable names just to allow for consistency with other bits of code, but they fill in the values here. And since this is once again doing a numerical integration, they need to provide the deriv function. Here we've still given them the template of the deriv function, that we provide less of this as time goes on. They are required to add some parameters to the call and add in the actual derivatives for radius, radial velocity, and phi. They do the integrator call on their own. So give them some prompt there, but they do that themselves. The plotting, in this case, we're still giving them some of the structure of the plots. This is one of the first times they've actually used subplots to do multiple plots together, which is why we're giving them more material here, but they're doing a lot of it on their own. And this is also the first time polar plots are introduced. So we teach them a little bit about polar plots. We also, this is a time where we might point students to the documentation online. And that's another skill that we're trying to build, is giving them enough information in the notebook to give them a start, but helping them access other resources. So they compute this for a circular orbit, and then we ask them to do the same thing for an elliptical orbit. You see we've now stripping out more stuff, just a little bit of instruction. And then one of the fun things about this lab is it allows us to move from thinking about a reduced mass going around the center mass to actually visualizing the motion of the 2 bodies. So at this point, I'm going to switch over to the instructive version so you can see the output of these plots. So a circular orbit looks like a circle. Here's the results for the elliptical orbits. So there's the ellipse of showing how the reduced mass position changes. And here it is for the two masses, the more massive M1 and the less massive M2. And then this is fun. We allow them to do animations, or maybe allow is the wrong word. We prompt them to do animations several times throughout the course. This is one of the earlier times that that's being prompted. So we're still providing a lot of the code here. But what we want them to do is think about how many frames do they need and how much time should those frames be given. So they do some calculation here to figure that out. And then within the animation call, they figure out how to plot the orbits. They figure out how to set the position of the masses at each frame. And then we provide them with the actual call to func animation. And the result is a pretty cute little movie, which nicely shows conservation of angular momentum right here. And I taught this lab just last week. I had a number of groups that ended right about here. They got to a pretty nice closing, which I guess I have one group that ended right here. My other two groups got slightly farther that I'll show. But we also have hyperbolic orbits that they can do. Notice this part is grayed out because the coding work is essentially the same. It's just showing a different set of initial conditions. There's our hyperbolic orbits. And then to reinforce the skill on reading data from a file, we also show them how they compare the results for this two-body integration to the actual motion of Pluto. So here we provide them with data from the NASA Jet Propulsion Laboratory, stored as a separate CSV file. And they read in this data, and then they compute Pluto's orbit using their own numerical integrator, assuming that it's only the Sun-Pluto system, and compare these two together, and it's a pretty nice agreement within about 0.7%. And the final portion of the lab, which I guess 2 out of my 4 groups got to this one. One of them got through the elliptical orbits, and the other one completed all of it. So this is the final portion, allows them to try out this non-Keplerian orbit with a 1/r to the 5 law, as Paul pointed out. And essentially, they just adapt their derivative function here to include this new force. And the resulting orbit is quite cute. And it shows the value of numerical integration, that it can allow you to solve problems unlike what they could do with pencil and paper. As before, there are some challenge problems at the end. In this case, it's about energy and about Kepler's third law. Any questions as I move back to the presentations?
Jeff has okay.
I just want to ask about, I like how you have it paced out so that like some students will make it to this point, others can go on and challenge themselves. Do you factor that into your assessment then? Like the students aware that like, okay, I can't really give you this problem because only 2 of you got to see it.
Yeah. Oh, you mean like exams and so on?
Whatever
Yeah.
methods you're using, yeah.
Yeah, so kind of 2 separate questions here. The first, which is what I thought you were asking, was how do I assess the lab grade if some students get farther than others? And it's this is instructor specific. What I do personally is I ask that students work hard and work well within that 3-hour block, that I see thoughtful analysis, that their code is clean, that they are using meaningful variable names and doing calculations with variables as opposed to on their calculator, that type of coding hygiene. And that will get them a pretty good grade, like an A-. And then they need to do something extra, which could be doing some of these later, harder exercises, or just doing a really good job on the core part in order to get an A score. As far as how this goes into exams, I'm also teaching the lecture course this time. I don't have every year. But I would say the exams are primarily focused on lecture content, but the types of work that they do in lab help support their conceptual understanding of that. Probably the most lecture style content that they see in lab would be Taylor series, which really is primarily introduced in the lab. And in that one, they also see, although I don't go over it in lecture, they have homework problems that ask them to use Taylor series. So I would say anything that shows up in exam has been introduced at multiple points in the curricula.
Can I just ask a quick follow-up since I opened that can of worms?
Yeah.
Are you keeping it then kind of as a, I don't want to say standalone, but more or less separate entity from lecture when you have this designed? Is it kind of like a one credit? I mean, you've
Oh,
said it's a one credit lab, but I just didn't know how like integrated they were together. Are they always concurrent with each other, that kind of deal?
yeah. So it's not a 1 credit lab. It's a 0 credit lab. They receive 1 grade, which is for the lab lecture combined, and that's just standard on how we handle labs at Grinnell. It's 15% of their final lecture grade comes from their performance in lab. And for that reason, because we aren't giving credit for this lab, we've never taught it separately from the lecture. I imagine that could be done, but it'd have to be done after the students had seen the mechanics content. It relies too heavily on the mechanics content to be done otherwise. In terms of like in ways they diverge, the biggest way is that we have different instructors. So again, this is normal for Grinnell labs, but the lecture instructor is not necessarily, and maybe not usually, one of the lab instructors.
So we normalize grades, and there may be a waiting toward the final project to see how that all goes.
Yeah. Yeah. So the final project is one of the big components of their lab portion of their grade. There we go. So we have been studying this. We've actually been running this as a lab for, I think that this might be the 10th year right now. And this is data from attitudinal surveys, this is 2 years worth of data. I have quite a bit more data than this, but it hasn't all made it into the analysis yet. We administer these surveys at the beginning and towards the end of the semester. So I'm showing some of the questions that are asked. Each pair of lines corresponds to one question. The top line is before the question was asked, and the bottom line is after.
The lab was run.
Yeah.
Okay.
Okay. And the colors correspond to their answers. So strongly disagree is orange, strongly agree is blue. And in general, we want more blue in the second set of the pairs of lines. So for some of these questions, so these first two are really about students' sense of self-efficacy. So compared to other students, I feel I know a lot about computers and I can usually figure out a way to solve CS programs or problems. And we see a little bit of growth throughout the semester. It looks promising. But where we see the most growth in the semester is when they're actually asked, could you do this thing? So those are the final 4 questions. I'm able to program a computer to plot data, able to program a computer to numerically solve a differential equation, able to explore a physical system by varying the relevant parameters in a simulation of it, and I'm able to use a computer to compare data to a model. And students are much more confident on those towards the end of the semester, and that fits with our sense of where they are as a class. We also survey just how much they enjoy or found the lab useful. And so the blue is the responses to I found this lab useful, and the orange is I enjoyed this lab. And most of the students are in the agree or strongly agree camp. I'm actually always delighted with how many students really just enjoy being in the lab, especially considering that so many of our students have these insecurities around programming. They tend to find it a fun experience.
Can I just ask a question real quick?
Yeah.
What you said this is mostly physics majors, but you have some computer science students. Do you have a sense of what the fraction is of just pure physics majors versus computer science majors or double majors?
Right. So we rarely have a student who is not also a physics major. Probably maybe a couple each semester, 1 or 2. And they might be CS or they might be math or chemistry even sometimes happens. In terms of fractions of students who are maybe dual enroll or dual majors within CS and physics, I'm going to hazard a guess out of nowhere and say 1/5.
I was going to say 20%, so I think we're on the same page.
Yeah, so maybe it wasn't a guess out of nowhere. Let's see, I see another hand up too, Joe.
Yes. Do your students get any computational experience in their introductory calc-based physics courses?
This is a this is a good leading question. We're going to talk later on about how we see it throughout the curriculum. Short answer is they do not get any programming beyond Excel manipulation within their first 2 semesters. And I should note that we don't have a separate track for physics majors from non-physics majors. All of our pre-health and biochem and bio students also take the same set of first 2 physics courses. I think previous to my time at Grinnell, there was experimentation with adding Python to those, and
it didn't end well. It didn't start well, actually. I think that was actually well, okay, it was a term faculty member who refused to learn Excel, which is a prideful position. Yeah.
Let me
Thank you.
return to that point later on. All right. So I've shown you the survey data. We've also been doing some interviews with students. This was a project where we took the interviews last semester or last year. They've been transcribed and coded, but the analysis is still in the works. But I wanted to highlight some of the quotes from this. Again, these are interviews that were conducted at the beginning and the end of the semester, but I'm showing you quotes from the end. So it's easiest for me to understand physics with pictures, which is part of why the lab is so helpful, because it has graphs and it has pictures of what's going on. I'm more comfortable with programming, definitely, because of the amount of practice that I've had with mechanics labs. So now I'm getting better and trying harder and learning new methods. It's kind of like reassuring, I guess, that I can learn something pretty new. And I selected these quotes in part because these are lovely quotes, but also because they illustrate some different areas that we want to analyze. So one is, are the students getting any better physics knowledge from completing these labs? Are they able to draw connections between what they're seeing in lab and the actual physics? And it sounds like they're finding these visualizations helpful for that. We also want to know, do they feel like their programming skills are improving? Gets at the second quote. And then finally, we're interested in what this does to students identifying as a physicist. Does it make students feel more confident to have this other tool set, or does it lower their confidence level if they're struggling through lab? So that's why it's good to see students who might have had a little bit of a difficult time at the beginning, but are finding that they can persevere and make this code actually work. Okay, one takeaway though, should go back from this interviews and from our own observations as professors, is that students exit mechanics lab and they're still kind of shaky on how they could do their own completely unscaffolded work. And that is a big motivation for including the final projects where they get to try to develop their own program, but it's also good motivation to including programming elsewhere in the curricula.
Yeah, so we have I guess I'm here to talk about backward diffusion. We have a modern lab course, a modern physics course that has a lab, and probably a third to 50% of the labs are now all done with Python control of voltmeters and ammeters and the like. We don't expect the students to do that skippy programming, but we provide the framework, and then along the way, they learn a little bit about plotting, and they learn a little bit about arrays and saving data and saving figures. And so actually it has been quite useful to those who teach mechanics lab that students have already gone through a little bit of Python. They never had to code anything directly, but they got to see how the notebook worked. And I think that's a terrifically valuable thing because they're actually dealing with data. And so that's kind of useful. Then later in upper level labs, we have a kind of a second semester E&M and waves class. And again, we have maybe 30 to 50% of those labs are done with Python. And, I think students by then have long abandoned Excel, and they are reading in the data that's presented. And part of it, of course, is you make sure, we used to take 12 data points, we now take 3,000. And so it makes it pretty pretty obvious that the low energy path is to stay in Python and work with that notebook, for example, or extend their own.
And the other area that we've been incorporating programming is into our upper level theory courses. So one of the great benefits of having students see this mechanics lab and their sophomore year, and also see Python within the context of the modern physics course, is that then we can actually give them homework assignments that require programming. And that has primarily happened in the electromagnetic theory course, though we've also been incorporating it into our astrophysics course. There's been some motion and thermo, and then quantum as well. And here's an example of one of the homework assignments for the electromagnetic theory course. And this is a movie showing the method of relaxation in order to solve for the electric potential subject to boundary conditions. So a classic algorithm here. And these we implement somewhat differently. These are assigned as homework. When I've taught this course, I've allowed students to do this homework in pairs or to do it individually. And the notebooks themselves are less scripted, though we still provide them a fair amount of code, aside from the final project. And they give students practice visualizing some more complex situations. So here's electric potential, but we've got one that calculates flux through a variety of different shaped Gaussian surfaces. We've got one that uses Biot-Savart in order to integrate to find the magnetic field produced by a current. So I'm talking about these in part because this is one of my current projects, but more importantly, because I will be posting these to PICUP. So if you're interested, this summer, there should be some more exercises on PICUP that have to do with EMT. All right. If you're interested in the mechanics stuff, this is available through our textbook, which came out, I guess, last year. And I have here all the chapters, so you can see all 29 of them. The actual units start in chapter 5. And you can see that the final 3 are some appendices that we've included. And these provide just some more in-depth information on some key topics, such as numerical integration using solve IVP, input and output, and creating animations. Questions?
So I have a question on just sort of how this fits into your curriculum. So in essence, you're using this lab to introduce computation to the students. Do you have a computational physics course, or is this it? Is this where they get the computational sort of kick in the pants?
Well, this gets back to where yes, we have a computational short course, well, a 2-credit kind of every other week course, or we meet, I guess, once a week, but it's low. No, it's 2 credits. And it covers some of the same topics, but it has numerical methods and in Monte Carlo methods. We cover radioactive decay for that, or perhaps financial modeling. I don't know which. And I think decay is in the order here. And but that course has become deprecated a little bit because we use that teaching to staff the labs. So I think that's really what's happened. So this, in a way, is it. And then otherwise, we don't have a formal computational physics class.
Yeah. So the 2-credit computational physics class was initially thought, well, there would be no need to offer it again. But occasionally students get really excited and we have enough staffing. So it gets offered every few years.
They badger us. We comply. Oh, and by the way, that computational course had started life pure 35 years ago, pure Excel, just for the fun of it, because it was accessible and it was readily available. Then it went and morphed into Mathematica and then MATLAB. So we were kind of doing all 3. And now I kind of have shoehorned it into Python because that seems to be the direction we're running. Although for historical reasons, I keep the Mathematica and the MATLAB in there so we can all remember where those colons go and whether you, oh, what else? Yeah, all the other little syntax differences.
I just wanted to ask, well, generally, I want to ask kind of the dirty question of, have you encountered many issues with AI? And I ask this because we recently implemented a course that I could not come up with a good name for, but it was basically meant to be intro programming for scientists. As you mentioned, the intro sequence of CS was useful, but didn't get to quite the points you'd necessarily want. Mainly the plotting, the visualization, the reading data in and out. But even something like Colab now finishes code so quickly with you, and it's so easy to find the code that's out there. My group was good, but it's really hard to navigate that. I didn't know if you ran into any issues or if you came up with some magic weapon that could actually solve this.
Right. So part of the magic weapon is that students are doing this, at least for mechanics, they're doing it in lab with instructors and student assistants hanging around. For something like the electromagnetic theory homework assignments, that is a question. So far it hasn't, I haven't worried too much about it, mainly because I'm still primarily interested in their physics knowledge and just what they can do. So I'm still in the camp that if they can find code and get it to work and modify it appropriately for those electromagnetic theory assignments, that's okay for my learning objectives.
And document it appropriately.
Yeah.
So, right, the magic is that AI does it for you, and then there's no explanation. And so we really want them to document their code.
The other, I mean, this does raise a bigger picture, which I know our CS department is talking about as well, which is what is the place for instruction in programming when there is AI available? Like, is this course even necessary now that students can use AI? And I actually think that the way that our lab is structured with these notebooks that students are working through is a really good way for students to learn programming within this environment, because they are always going to have snippets of code available that they can work from and modify and test. But what they need to be able to do is read it and interpret it and have some sense of whether it's actually doing what they need it to do. That is something I'm considering and thinking about.
Right. And we, by the way, we do have open internet here so that during lab, if they need to go to Stack Exchange and figure out the syntax for save text, or remember that when you're peak finding, you need to get the 0th element will actually give you the stuff you want. All of that is Python's help facilities are okay and slightly getting better. It has the worst bedside manner when you make an error. And so it's often useful for students to have that available just to look up. So it's not unusual for that to be happening in lab at the same time.
And in fact, I encourage it. Students come to me with questions and I will demonstrate how do you look at the Python documentation and understand what this function is calling. If you can't figure it out that way, how can you Google it and actually read the Stack Exchange responses? Because that takes practice and a certain level of familiarity with both programming in general and Python specifically.
And of course, Python changes every year. And so even that, we have to keep up with it. And so that's why we modify the instructor ones to make sure that they're still working. So for example, between 3.9 and 3.11, Python is now very fussy about, or matplotlib is very fussy about escape sequences. And so you have to modify your code for that.
Jeff, I'll just I'll plug myself here. We're currently looking at doing a webinar probably in the fall about AI issues in coding, and I am currently running a computational physics class where I am leaning hard into having students use AI, and so I will have feedback. and thoughts at some point.
Well, thanks.
So you're,
I mean,
you're embracing it. I see.
Yeah, I'm taking the viewpoint of I cannot stop it, and so I may as well just lean in.
anecdotally, like my general issue is I understand and I have software engineering friends, and we all agree that you're going to just go to Stack Exchange for some things. Like you need to learn how to do that if you're going to be programming something. Um, I've encountered very few students who have managed to use AI helpfully. Like there's kind of that difference of like, are you cheating with AI or are you just using it as a resource? And that boundary there seems to be something that some students have trouble finding, and encouraging it. And so that I'm just on I'll be paying attention to your event coming up, Nick, just because I'm constantly trying to find where to find that boundary and how to keep students from jumping over it too much.
And it wasn't AI, but I do recall a student doing a project on a double pendulum and it wouldn't run and it wouldn't run. And I said, where did you get this? And it turned out that there were some hidden HTML tags in there that were corrupting everything. So at least with that student,
Yeah.
we learned a lot about using Notepad++ to strip out various things. And we had a nice little talk.
All right. Well, on that note, we are at the hour, so I think we'll stop the recording and thank Paul and Charlotte for the presentation. So thank you very much.
Thank you.
Thank you.
Yes, thanks for the questions.